All right, sorry. Now we can actually record it. So, first of all, how many carbons are in my Grignard? Let's make sure that we can count carbons in the Grignard. Who thinks there's 1 carbon? Who thinks there's 2 carbons? Who thinks there's 3 carbons? So there's only 2 carbons, right? So kind of like how an alcohol group would look on there. I know that that OH group is attached to a carbon, right? There's no carbon here. So just, again, making sure we know how to count carbons in our Grignard. All right, and then I have these originally, I'll use the same color coding. Let's use purple. 1, 2, 3 carbons in my aldehyde. All right, so I'm gonna start by drawing those 3 carbons. And now that carbonyl carbon, it used to have a double bond to the oxygen. What am I going to change that to? Just a single bond. So there's my OH group. And now I'm going to add these 1, 2 carbons to that same, what was formerly my carbonyl carbon. All right, I kind of drew this in this weird kind of kinked way. If you had just drawn that would have been equivalent, right? I kind of copied based on what my starting material was. That's why it's that weird kink shape, but those are 2 equivalent molecules, just drawn a little bit differently. But importantly, I have added these 1, 2 carbons to my original 1, 2, 3 carbon aldehyde. Okay? Because we're growing our chain here, remember, like I told you, one of the best ways to make sure you're not going to make a stupid mistake is to count carbons, right? That's going to be increasingly important here because we're going to be growing our carbon chain. We want to make sure that we've accounted for everything, all right? It's not a bad idea when you're starting out and doing these problems to grab a highlighter and color code things so you can see what's what from your starting reagents to your products, keeping track of what carbon's what. All right, so now let's make it a little bit more difficult. We'll actually take that same aldehyde, but now we're going to use a Grignard like this. All right, so now again, I have my 3 carbons, from my aldehyde. That formerly, that carbonyl oxygen is gonna become oh my God. What's my new functional group I'm gonna get in my product? Alcohol, so it's gonna be an OH group, okay? Now I'm adding, in this case, my Grignard has 3 carbons, right? But importantly, it's that carbon that was attached to the magnesium. That's where my new bond's gonna be, right? So when I'm gonna add this 3 carbon group here, importantly, it's gonna be added. These are my 3 carbons, and again, the new bond is between what was formerly my carbonyl carbon and in my Grignard, the carbon with the magnesium. All right, this one right here. Cool, all right. And just to kind of like, again, take a step back, it's a little weird to teach this in this particular chapter because you're starting out with, on the one hand, your reactant is an aldehyde or ketone, and your product is an alcohol. But importantly, the solvent that this takes place in is an ether. Okay? if you did like the 2-semester organic chemistry course, no doubt you would be doing these types of reactions in the lab. They work really, really well. They're relatively cheap, all things considered. And again, they create like new carbon-carbon bonds, which is not something that very many organic chemistry reactions do. All right, so they're relatively robust in that sense. Okay. We're just going to do a whole bunch of examples here. Make sure we got this down. Again, one of the things that makes these Grignard reagents so powerful is this, like, if we just do the generic R, Mg, Br, there are no limitations on what that R group can be, right? So this is an example where my R group is a benzene ring. All right, so again, I have these let me use the same colors. These 4 carbons, that's what I'm going to start out with. What was formerly my carbonyl carbon, now instead of having that carbon-oxygen double bond, it's going to have a carbon-oxygen single bond. And now I'm going to attach what's on the back end of my Grignard, which is in this case going to be this big, ugly benzene ring. All right. Importantly, let's count carbons real quick, because I feel like this is an easy place to accidentally insert a new carbon or something like that, right? So I start out with my 1, 2, 3, 4, 1, 2, 3, 4, and then I have the 1, 2, 3, 4, 5, 6 carbons on my benzene ring. All right, it's kind of easy to accidentally insert an extra carbon or something like that. So make sure to do that, double check. If you ever see me doing organic chemistry, you'll see me like tap the page a million times. I'm just always counting carbons, all right? Good double check. All right, so now let's mix things up a little bit. See if you can't give me, there's 2 different options that you could do. Either one of them, go for it. You're going to tell me what reagents I could use to create this particular product here using our Grignard reactions. All right. So there's actually 2 ways to do this. All right. There's one thing that we could say right off the bat is this carbon right here. Instead of having this carbon-oxygen single bond, I know it's going to have a double bond, right? It's going to have that double bond at that particular carbon. Now, the reason why there are two different ways to do this is I can either say that this is my new carbon-carbon bond, right? So that means that my starting aldehyde would be this here, right? If I'm saying that's my new carbon-carbon bond, then these two were originally in my aldehyde, which means that these 1, 2, 3, 4 carbons are from my ether. Not my ether, I'm sorry, my Grignard. Right? Or I could say this is my new carbon-carbon bond. So everybody take a second and draw me the reagents that we would use if this was my new carbon-carbon bond that I was forming, the one that has this yellow arrow pointed to it. What set of Grignard and aldehyde or ketone would you use? That means that these 1, 2, 3, 4, 5 would be my aldehyde. And this 1 carbon would be my Grignard. Right, so either one of those I could use to create this alcohol using my Grignard reagent method. Take a second and see if you can't give me my reactants that I would need for this particular product. There's only one way to do this one, right? All right, so again, my strategy is I know this carbon right here, because it has that OH group bound to it, it has to be that carbonyl carbon, right? It has to have that carbon-oxygen double bond. In this case, because this is a ring, the only choice for my new bond is this one right here. Without, I guess without any like weird intermolecular stuff going on. So my ketone would be this one right here, my 6 carbon ring, and my aldehyde, my Grignard, how many carbons? 1, 2, 3, 1, 2, 3, MgBr. Okay, so most reactions that we've learned up until this point, we just needed to be able to go the one way, right? We needed to be able to predict products given a set of reagents. These ones are a little bit more complicated. Now we have these new carbon-carbon bonds, and we're like upping up the skill level here in terms of what I expect you to be able to do, which is, in this case, being able to predict what reagents you would use, what starting reactants you would use in order to create a particular product. Okay? So, real quick, if you have not already, I have your exams from, before spring break to give back to y'all. In general, exam scores did dip a little bit, and so I went back to, not forever, this is not like universally speaking, but generally speaking as a class, and I went back to see those students who did fairly well on the first exam and then didn't do so well on this exam. And pretty much across the board, it was because people stopped doing their homework, all right? Nobody in the history of the world has ever learned chemistry without doing homework about it, without practicing. You have to put pencil to paper and work through problems. You can, like, all right, best piece of advice I ever got was from a math teacher like my sophomore year or something like that. And it stands for all sciences. And he was basically like, look, when I'm standing up here walking you through it, it's all logical. So you're going to be able to be like, oh, yes, okay. Oh, yes, I see. Yeah, sure. And then you go to do it yourself, and you're like, wait, what the hell? What's going on here? It doesn't really work. It's not the same thing. Being able to follow along with me up here and doing it yourself are two completely different skills, right? It's one thing to be able to follow along logically. It's another thing to be able to do it yourself. So if you're not trying to practice, you're in trouble, basically. All right? I know that these online homework systems aren't everybody's favorite thing in the entire world. I understand that they have their own little quirks that are frustrating. You get one little thing, one little hydrogen wrong, and it tells you you're wrong, and it's like, oh my God, that's the stupidest little mistake. It's driving me nuts here, all right? However, there is one humongous benefit to these systems, and that is you get immediate feedback about whether or not you're doing it correct. If you really know what you're doing, it's not the system that's going to be stumping you. Right? When I'm helping out students, it's not the system that's screwing them up. It's just that they don't know how to do the problem. Right? So 99% of the time, you can't really blame OWL. It's your own understanding of it that's going on here. All right? And if you are stuck, just screenshot it and send it to me, and I'm happy to walk you through it. Right? But the bottom line is you have to be doing the practice in order to be able to do it on the exam. It's just how it works. There's no way to do it without having some sort of practice involved. All right? And again, I know these systems are frustrating, but like again, that immediate feedback is really valuable. When I was a sophomore taking this sort of level class, we had 3 exams and a final, and that was the only graded material in the entire course. There was 0 feedback that you got about whether you were doing something right or wrong. So you walked into that first exam like, man, hope I understand what's going on in this class. Like, I mean, it was like 0 feedback whatsoever, and that standard's kind of changed over time. But nonetheless, I know it's frustrating, but that is the practice. Everything that's on that exam, I can point back to a particular OWL assignment where that skill was practiced, right? So these problems are sort of picked specifically to get you practice for what will be on the exam, all right? Anyways, you got to do the homework in order to understand the material. If you're not happy with your exam grade, but you didn't do the homework, that's 100% the reason, all right? Okay, so let's continue with this here. Some quirks about the Grignard. Well, so first of all, one of the things about these Grignards that are kind of going to be a pain in the butt is now we have like this way to do kind of more complicated problems, which is we actually know how to make this guy right here if we started out with an alcohol, right? Let's go back to our alcohols chapter real quick. Let's remember that we have these oxidation methods. Actually, this isn't the best slide. Let's go back to where we specifically talked about oxidation. All right. So we have these 2 reagents, this sodium dichromate. And remember, I told you that really what you want to spy is this chromium here. Chromium means oxidation. If you ever see a reagent that has chromium in it, it's going to mean an oxidation reaction. The other one that you would see in addition to sodium dichromate is CrO3, and it does the exact same thing. All right. So again, when you see chromium, you're thinking these oxidation reactions. So we know how to take an alcohol and oxidize it to a ketone, which means that now we know how to take that ketone and do another step to it, right? We have this sort of now this ability to do these multi-step sort of problems, starting with an aldehyde, converting it to a ketone, and then hitting it with our Grignard reagent. All right, so let's see an example of what that might look like. Let's go back. So what do I mean? I can do something complicated like I'm going to take this alcohol and I'm going to hit it with my sodium dichromate. You don't have to remember all of these reagents, but these would have been the other ones there. And so what is this going to do? This is going to oxidize my alcohol and convert it to a ketone, right? And then I can go ahead and take this ketone and now hit it with this Grignard reagent. And so everybody take a second and draw me my product here. All right, so how many carbons are in that Grignard? 2. All right, so starting out with my aldehyde, or my ketone actually in this case. 1, 2, 3, 4 carbons. Now what was formerly my carbonyl oxygen is that OH group. And now I have 2 new carbons that came from my Grignard. Okay. I've been kind of lazy up until this point, just drawing my one Grignard reagent. If I'm going to do my full list of reagents here, you would actually see it's done in 2 steps, where that second step is to follow it up with acid. It has no real practical application for like what we're going to do. If we learned mechanisms, like if we were in the 2 semester, that acid would play an important role in the last step here. For our purposes, it's just going to be that list of reagents, right? So if we see them on our constants page or whatever, it's going to be step 1, Grignard, step 2, acid. Okay? So let's see. Let's do another one. Oh, shit. That's not what I want. All right, so see if we can't fill in the blanks here. All right, PCC. What the heck is PCC? It's a weak oxidizer. So another one of those oxidizing agents. Importantly, it will convert a primary alcohol into just an aldehyde. That looks ugly, but whatever. Okay. So again, I'm oxidizing my alcohol, this time using a weak oxidizer, which will convert a primary alcohol to an aldehyde. And then I'm going to hit it with this Grignard, which will again take my 1, 2, 3, 4 carbons, but now add what's on the other side of that Grignard, which, oh, that's a little brutal. Upside down pentagons are hard to draw. Anyways, that's what I'm going to be attaching there are to my 1, 2, 3, 4 carbons. What was formerly my carbonyl carbon now has that alcohol group on it and also has the 1, 2, 3, 4, 5 carbons from the back end of my Grignard.
So the H3O doesn't do anything?
I mean, it's not anything, like, generally speaking, truthfully, this H right here comes from that acid. That's the role of that acid. But for our purposes, no, it's not really doing anything. Again, you'll see it when you see that list of reagents on your constants page. That's what you'll see. All right, so one more thing we're going to have to make a note about with our Grignards. Again, they're put in this chapter because the solvent that you use is that ether, right? Importantly, again, if we look at the structure of that ether, right, that oxygen has all single bonds, right? It's sandwiched between two carbons. So again, this is our solvent. Importantly, we're going to make a note. No water with Grignards. Okay. It's one of the only pain in the butt things about, again, these reactions work very well. They're very efficient. They're very cheap to do. The one sort of particular thing about it is you need to make sure that you've got every bit of water out of any glassware that you use, or any sort of solvents have been dried to make sure there's no trace amounts of water. Water and Grignards do not mix, okay? If we take a Grignard reagent and we add water to it, what ends up happening is that Grignard, that MgBr, gets replaced with just a hydrogen. Okay? Grignards turn out to be strong bases as well. So if there's any sort of source of proton around, they're going to snatch that proton, and you have just taken this very roundabout way of creating an alkane, right? Which is not what you want, generally speaking. If you want an alkane, there are millions of easier ways to get it than going through this Grignard route. Okay? So importantly, if you ever do have any amount of water in with your Grignard reagent, it will, again, sort of just like chop that MgBr and replace it with a hydrogen. Okay? All right, so we got a little bit of time. Let's do a little bit more practice here. This time we'll have so you're going to tell me what's missing here. And then what Grignard would I need? No, we just did that. Right, so you're going to tell me what product am I missing from this first step, and then what reagent I would use in order to create my final product here. Right, and do me a favor and count your carbons. Specifically in your Grignard, make sure you have the correct number. All right, so this first step here, again, I see that chromium, so I'm thinking oxidation. Just going to convert that alcohol to a ketone. Now the question is, what am I going to need to use in terms of my Grignard? So if I kind of work backwards here, you can note that these 1, 2, 3, 4, 5 carbons, got those here, which means that my Grignard is going to contain these 1, 2, 3, 4 carbons here. Right, so my Grignard and again, if I'm going to double check count carbons, 1, 2, 3, 4 carbons. Cool. All right, so again, these Grignards, they use ethers. We haven't even really talked about ethers yet, other than the fact that they are used as solvents in these particular reactions. These reactions here are going to be important in this particular unit because, well, A, we have our ability to predict products, which is what we've always said about reactions, but now we also want to be able to predict reactants, be able to determine which Grignard reagent we need to create a particular product. All right, so we have this added complication of having to kind of like work backwards here, given a particular product. All right, cool, so we'll be done there. I still have your exam.